Almost every statistical shortcut you have ever used quietly assumes one particular shape. And most of the time, you never once asked whether your data actually has it. The 2/3 rule from standard deviation assumes it. A lot of the tidy targets and the alerts and the control limits buried in your analytics tools assume it. That shape is the normal distribution, the famous bell curve. And today, I want to talk about what it really is, why it shows up in some places and flatly refuses to appear in others, and how to tell with your own numbers open in front of you whether you are allowed to lean on it or about to be quietly betrayed by it. I am not a statistician. I am someone who runs small businesses and spent years assuming my numbers were bell-shaped, simply because that is the only picture anyone ever draws. I planned around averages as if most customers sat politely near the middle and then watched my real orders clump low and trail off into a long tail that no bell would ever produce. So this is not a lecture on probability theory. It is the plain habit I now use to check the shape of my data before I trust any rule that secretly depends on that shape being there. What the normal distribution actually is. The normal distribution is a specific bell-shaped curve that describes how a lot of naturally varying things scatter around their average. Picture a hump in the middle where most of the values pile up, falling away smoothly and evenly on both sides, with fewer and fewer values the further out you go from the center. It is not just any mound of numbers. It is a precise, symmetric shape. And that precision is exactly what lets all those handy rules work, right up until the moment your data turns out not to match it at all. There are three things that make it normal. Three features define this shape. First, it is symmetric, so the left half is a mirror of the right, and the value above the average is just as likely as a value the same distance below it. Second, it has a single hump in the middle, one clear peak rather than two or three lumps. Third, and this is the real giveaway, the average, the median, and the most common value all land in the same spot, dead center. When those three numbers drift apart on your own data, that alone is a quiet signal that you are not looking at the normal distribution. The rule everyone borrows from it. The reason this shape matters so much is a rule you have already met. On a normal distribution, about 2/3 of your values sit within one standard deviation of the average, about 95% within two, and very nearly all of them, about 99.7% within three. That neat ladder is where the 2/3 rule comes from. And it is genuinely powerful because it turns a single standard deviation into a map of where almost every value should be. But read that opening phrase again. On a normal distribution, the whole ladder is built on the shape, and it collapses the moment the shape is wrong. Why the bell shows up at all? So why does the world keep drawing this one particular curve? The honest short answer is that whenever a value is really the sum of many small, independent nudges, none of them dominant, the totals pile up into a bell. Human heights come from countless tiny genetic and environmental pushes added together, so they land in a lovely bell. Measurement errors, where dozens of little random slips add up, do the same. Anytime your number is secretly lots of small unrelated effects stacked on top of each other, the normal distribution tends to appear, whether you invited it or not. Informations and is there. Here is the catch that matters for a small business. Most of the numbers you actually care about are not the sum of many gentle pushes. They are dominated by a few big forces, and that breaks the bell completely. Revenue, order sizes, time on page, days to pay an invoice, customers won per referral. These clump hard against the floor of zero and then trail off into a long tail of whales and stragglers. They are lopsided, not symmetric, with the average dragged well above the median by that tail. That is a skewed distribution, and it is the true native shape of most business data, not the bell you were quietly picturing. How to check without any maths? You do not need a fancy test to catch this. You need a picture and one comparison. First, draw a histogram, which just sorts your values into buckets and shows how tall each bucket is. A normal distribution looks like a symmetric mound. Skewed data looks like a wave leaning hard to one side with a long thin tail stretching away. Second, put the average and the median right next to each other. On a real bell, they sit almost on top of one another. When your average sits noticeably above your median, you have a right skew and a tail of big values. And the normal rules are already off the table. A founder-sized example. Let me make it concrete. And please treat these as illustration, not numbers to copy. Say your orders average $40 with a standard deviation of 30. Borrow the 2/3 rule blindly, and it suggests most orders fall between $10 and $70, and that a fair share should sit below 10, even below 0, which for a real shop is nonsense, because an order cannot be negative, and most of them cluster near a small typical value with a few big ones stretching the average up. The rule did not fail because the arithmetic was wrong. It failed because you fed a bell-shaped rule a distribution that was never a bell. What quietly breaks when you assume it. This is not academic, because the wrong assumption leaks straight into real decisions. A target set at 2 standard deviations will flag far too many perfectly ordinary orders as unusual when your data is skewed. An alert that fires whenever a number leaves its expected band will cry wolf all day long. A forecast that treats next month as a tidy bell around its average will badly underprice the chance of a monster month or a dead one. Every one of these tools is fine on genuinely normal data and quietly misleading on the lopsided data most of us actually have. The bell has famously thin tails. There is one more reason to be careful before you trust the bell, and it lives right out at the edges. On a true normal distribution, the tails are astonishingly thin, so a value 4 or 5 standard deviations from the average is treated as almost impossible, a once-in-a-lifetime event. Real business tales are nowhere near that polite. A single viral post, a broken payment page, one enormous customer walking in. These produce shocks the bell would swear could never happen, and yet they happen to small businesses all the time. When your rare events land far more often than a bell predicts, you have what people call fat tails. And quietly betting your cash buffer on the thin ones the bell promises is how a comfortable model walks you into real trouble. The one place it is genuinely safe, there is a beautiful exception. And it is worth knowing, because it rescues a great deal of everyday analysis. Even when your raw data is wildly skewed, the average of a decent-sized sample behaves almost normally anyway. Take 50 random orders and average them, then do it again and again, and those averages pile up into a bell, even though the individual orders never would. That is why the confidence intervals I talked about earlier can lean on a bell shape for the average of your data without ever pretending the underlying orders are bell-shaped. The trick is to remember the normal shape belongs to the average of the sample, not to the raw values underneath it. Measuring distance in standard deviations, one more idea rides on the bell, and it is genuinely handy. Once data really is normal, you can describe any single value purely by how many standard deviations it sits from the average, a number sometimes called a standard score. A value 1 standard deviation above the middle is unremarkable, while one that is 3 above is genuinely rare, out in that far thin tail where almost nothing lives. It is a clean way to say how surprising a number is, but it carries the same string attached as everything else here. The standard score only means what you think it means when the underlying shape truly is a bell. Do not force your data to be normal. When people first learn all this, the temptation is to torture the data until it looks bell-shaped, and I want to gently warn you of it. Yes, there are honest ways to reshape certain skewed numbers so a bell fits them better, and they have their place. But for the day-to-day reading of a small business, you are usually far better served by tools that never assumed a bell in the first place. The median, the percentiles, and the interquartile range I covered before. The goal is not to make your data normal. It is to stop reaching for rules that demand a bell when your data plainly is not one. Where the details live. Every one of these explainers lives in writing at dataresearchanalysiscollection. Come. The whole metric library in plain English, with the normal distribution drawn out on a real skewed set of orders sitting next to a genuinely bell-shaped one so you can see the difference with your own eyes. I keep it honest there for the same reason I keep it honest here. No promises about your results and no pretending a curve tempts a wild business. Read it slowly with your own histogram open, and you will start to notice how often the tidy bell everyone quietly assumes is nowhere to be found in your actual numbers. The honest limit, and hold the whole idea in proportion. The normal distribution is a model, an idealized shape, and no real data set ever matches it perfectly. It will not tell you why your numbers scatter the way they do, and it certainly will not fix a lopsided business by being assumed onto it. All that knowing the bell really buys you is the judgment to ask every single time whether the shape in front of you actually earns the shortcut you are about to take. A person who checks the shape first is worth far more than a rule that quietly assumed it and turned out to be wrong. So to recap, the normal distribution is a precise, symmetric bell where the average, the median, and the most common value all meet in the middle. And it is the hidden assumption behind the 2/3 rule and a lot of your tools. It shows up when many small independent effects add together, which is exactly why most skewed business data, dominated by a few big forces, never follows it. Check the shape with a histogram and by comparing your average to your median before you borrow any rule that needs a bell. And remember the one safe harbor, that the average of a large sample goes normal even when the raw data does not. Next time I want to talk about skewness itself, how to measure which way your data leans, and just how heavy that stubborn tail really is. I will see you in the next one.